So welcome to this video. We are going to discuss question from the book Verma from the chapter Capacitors. This is a rather popular question where we have two dielectrics filling a capacitor like this. K1 and K2. This is dielectric 1. This is dielectric 2. We have to find the capacitance of this combination using our uh, knowledge of capacitors. So we know that the distance between the plates of the capacitor is some d, and this is a square plate capacitor. So this h is a, so the area of the plates is a square. So basically how we select the elements is very essential to how we uh, calculate the capacitance of each particular part. So here we are going to take element like this, and this. The width of this element, we'll take that this element is at y distance from one end. This distance being dy, and the length of this element is some, let's say here the length of the element is some x, then this particular element, this length, we are taking as some d minus x. So if we take a triangle like this, take a small triangle, in that small triangle this vertical distance would be dx, and this horizontal distance is going to be dy. So this distance, this ratio dx by dy, that we basically want to evaluate first, because when we'll be writing the capacitance we'll use dy. That would be your width of the capacitor, or you used to not the width, the used to calculate the area of the plate of the capacitor. So we want dy in terms of dx, and we would also need the width of the capacitor, which would be x. So this distance dx by dy, this is simply if we see this triangle, in this triangle this would be x dx, or d upon a, or dy is equal to a dx by d. So this is one of the things. Now we'll calculate the capacitance of each of the capacitor and add them. So capacitance of each of the capacitor is DC1 and DC2. So it would be written like DC1. Right. So we will write DC1 is equal to area of the capacitor plates ADX into epsilon naught divided by the width, that is x, into the capacitance K1. Similarly, we will write DC2, it would be ADX for a dy again, dy, this is also dy into epsilon naught k2 divided by t minus x. So the capacitance dc is equal to dc1 to dc2 divided by dc1 plus dc2. So the net capacitance, so this value dc is equal to a dy epsilon naught k1 divided by x to a dy epsilon naught k2 divided by t minus x divided by a dy, that is common, epsilon naught k1 upon x plus k2 upon t minus x. So this a dy epsilon naught, we can get one of that. So this value becomes a dy epsilon naught k1 k2 upon x into d minus x divided by k1 into t minus x plus k2 into x divided by the same term x into t minus x will get into the order as well. So this will get cancelled. So this is the term which we have to integrate dc, and we have to replace dy as well. So dy we learned, dy was a dx by d. So this expression a epsilon naught k1 k2, it is outside. Inside we have a dx divided by d. D I have taken outside, divided by k1 d minus x plus k2 x. So this capacitance C becomes a square epsilon naught k1 k2 divided by d. And integration of ln, this is ln k1 k2 minus k1 into x plus k1d. So this k2 minus k1, it comes outside as well, k2 minus k1, and limits goes from 0 to a, because we have changed from y to x. The limit goes from 0 to t, right? So this value becomes capacitance C is equal to a square epsilon naught k1 k2 divided by d k2 minus k1 into ln k2 upon k1. After substituting value of t and 0, you will get k2 upon k1 ln. So this was the answer which we are looking for, that what is the capacitance of such a system where the dielectrics are distributed diagonally. So they have a ln expression k2 by k1 and this k2 minus k1. So thanks for joining and have a good day.